Assalamu alaikum. Welcome to the first online lecture in the lab portion of structural engineering. For this week, I have chosen only recorded lectures followed by small assignments. Today, we are going to start working on a two-dimensional truss analysis software. Today's task is not to complete the software but to understand the basics and initial working on the software. Let's begin with the lecture. This is one of very simple trusses that we have selected for this week's class. As you may know that whenever we use stiffness method, we begin with naming the elements and nodes. By naming, I mean giving them a number name. For example, in this particular case, element number 1 has been given name to the bottom element. Number 2 and number 3 have been assigned as element numbers to the other two elements. Similarly, each of the node has been assigned a number 1, node number 2 and node number 3. To solve a truss, first of all, we need to know the geometry of the truss. That can be done in two easy ways. Either we know the length and angle of each of the elements, or we know the coordinates of each of the node. Both can help us out. In this particular case, we are going to use coordinates as the geometry of the elements and definitely the truss itself, because even if we have length of the elements and their respective angles, we will have to convert them to nodes to calculate appropriate values of stiffness. So let's proceed with this example. This is the first assignment for your class. You have to analyze this truss, the truss that has been given. You have to analyze this truss manually and you have to share your solution with me in form of an assignment. You can solve it on the papers, take photos, and along with your registration number, create a PDF file, share with your CR, and CR finally can email the zipped folder containing the PDF files of all the class to me. So you are going to solve this truss in the same format as I have shown you, while we are going to proceed with the software. Today we are going to start with only input of the data. There are three input types that we want. Number 1 is nodes, input of the nodes, because these nodes are going to create the geometry of the truss. The location of each node along with the name of that node is required to be given as an input. Or in tabular form, we can say that this sort of table is required as an input, where we have the node numbers, and corresponding to the node number we have the x coordinate and y coordinate of each of the node. So this is what we want to give as an input. To input this data, we can utilize arrays where node ID can act as index or it can be stored even otherwise. Corresponding to each node, the x and y coordinates are to be recorded. So we have to begin with asking the user how many nodes do we have in the truss. N has been chosen as a variable to store the number of nodes in the truss. An input command can be used to take the input from the user, and you can have any message that you want. Later on we will use a for loop starting from 1 going up to number of nodes in the truss, and for each node we will demand x coordinate and y coordinate. In this particular case, I, the index, will act as the node number. X and y are two arrays that will store the x coordinate and y coordinate of the nodes. In this way, we will be able to store data as shown in the table above. Let me remind that we can choose a two-dimensional array as well. In this particular case, we have chosen one-dimensional arrays. X and y both have been kept separate. After taking input of the nodes, we will proceed towards taking input corresponding to each of the element of the truss. Corresponding to each of the element, we need at least 4 datas. Number 1 is modulus of elasticity of the material that we are going to use. Number 2 is cross-sectional area, the quantity of material which is being used. Starting node and ending node both are required. Remember that starting node and ending node means that we can calculate length and orientation or angle of the element both. Both of these things can be calculated easily. To take this data as an input, we are going to begin with asking user how many elements are there in your truss. Although it may seem that we can calculate number of elements from number of nodes, but not always. In the case that we have already considered a 3-element truss, yes, it is easy. 3 nodes should have 3 elements. But if there are 4 nodes, we can have 5-element truss and 6-element truss both. So we are going to ask user how many elements are there. Corresponding to each element, we have to demand user to input modulus of elasticity, a cross-sectional area, starting node and ending node. In this particular case, I have used individual arrays E and A to store modulus of elasticity and area for each of the element, and a two-dimensional array has also been used where J would mean the element number. However, I have stored the element number separately in column number 1 of the array called dir. Similarly, in column number 2 and column number 3, I have stored the node number where the element starts and the node number where the element ends. Later on, this dir j,2 and dir j,3 will be used to call the starting node, ending node number to calculate length of the element and orientation of the elements. After taking input of the elements, we have to move towards the next important input, and that is support data or support conditions. So we need this tabular form of data, node ID. Corresponding to node ID, we need type of support. There can be numerous ways of taking this input, but I have chosen this. User needs to input X if there is restraint in X direction. User needs to input 2 if the restraint is in Y direction. Both are rollers but in 2 separate directions. And if there are restraints in both the directions, user should input 0. In case of a truss, only 3 options are possible: roller in X direction, roller in Y direction, and a hinge support. To take this input, we have to begin with asking user how many nodes have sports on them, or enter the number of constrained nodes. For each of the node that has a constraint appended, we have used an array, two-dimensional array CONS. In column number 1, we have stored the node ID, while in column number 2, we have stored the constraint type. There are 3 types of constraint that we have created. 1 for roller in x direction, 2 for roller in y direction, 0 for a hinge sport. You can change the message to your liking. So in this way, we can take input of the sport conditions. Last important input is external force data. So we have to input this sort of table beginning with node ID, the value of force in x direction, the value of force in y direction acting on this node. So similar to previous examples, we have to begin with demanding user how many nodes have force or load acting on them. Corresponding to the number of nodes, we have created FORC named two-dimensional array, in which first column will contain the node ID where the force is acting. In second column, the value of force in x direction. In third column, value of force in y direction. If we consider the example at hand, when the user will input, he will input 3 as node ID. Value of force in x direction is 10, while the value of force in y direction in this case is 0, as it has also been shown in the table above. This is how we are going to take input of the data, which include node, their geometry, elements, all the data related to them, sport conditions, and applied forces or applied loads. After completing the input, we will proceed towards creating the stiffness matrix. So I have chosen the stiffness matrix here. So we all know this, you should know this matrix already: cos square, cos into sine, and sine square. That creates one portion of the stiffness matrix corresponding to each element. It is replicated here in the fourth quadrant, and its negative is considered in the second and third quadrant of the matrix. So this is what we have to code now, and we are going to consider this as maybe the last portion. E over L is to be multiplied with the whole matrix. So here we are doing it. First of all, we need to calculate E over L, and for that we need length of the element. For calculating length of the element, we will use the distance formula. Distance is equal to square root of x2 minus x1 square plus y2 minus y1 square. This formula is to be used to calculate length. So for each of the element, for example, we are using a for loop. For I is equal to 1 to number of elements for each of the element. The first line is Li. This array named L will contain the length of each element, square root of x2. dir I comma 3, the third column, and the second column contain the ending node and starting node of each element. Ending node and starting node, while x and y arrays contain the coordinates of each of the node. So for each of the node, x2 minus x1 means the ending node and starting node x coordinates of ending node and starting node square, plus y coordinates of ending node and starting node square. The square root of all of this will give us the length. Similarly, cos of the angle and sine of the angle can be calculated as the ratios x2 minus x1 divided by L, y2 minus y1 divided by L. So this is to be calculated for each of the element, and corresponding to each of the element we will calculate the stiffness matrix. So we begin with another variable which is equal to E A over L. E and A were taken as an input while we were taking the inputs for the elements. So we have to calculate these four components K11, 12, 21 and 22, where EA over L multiplied by cos square sine into cos, sine into cos, sine square. This square bracket will convert them to a matrix. The space will change the column number, the semicolon will change the row number. Hence we will have K11 matrix formed because of this code. K12 is equal to negative of K11, K21 is equal to K12 directly, and K22 is equal to K11. We know that already. Here there is one unique thing, that is another attribute appended. This I will differentiate between these matrices for each of the element. I will be equal to number of element. So whenever we want to call stiffness matrix at element level, this I will define the stiffness matrix for each of the elements that we can use to combine to form the global stiffness matrix for the whole structure. That is also called as the total stiffness matrix or the structure stiffness matrix. This is how we form the structure stiffness matrix. First of all, we have created a structure stiffness matrix containing zeros. Total number of rows and total number of columns are equal to 2 multiplied by number of nodes. That we know already. 2 multiplied by number of nodes are the total number of rows and total number of columns for the stiffness matrix for the structure. Now, I and J for each of the element, we have to first of all know I and J, which is equal to the starting node and ending node of the element. Instead of using dir n, 2, n, 3, I have stored them in another variable called I and J to make the code look less cluttered or less difficult. So this portion, you will be able to understand this portion left hand side only when you calculate after inputting the value of I and value of J that which portion of the stiffness matrix is being considered, and K11 from that element number n is replacing the previous value, actually not replacing, being added into the previous value. We know that along the diagonal we have to add the things, and off diagonal we can simply replace them with the previous values, although there should not be any previous values existing there. Up to stiffness, structure stiffness matrix is the task for today. I am going to end today's lecture with two basic assignments. Number one is to solve the truss that has been shown initially here. You have to solve this truss manually and share your solution with the CR. Later, you have to complete the code, try to complete the code up to structure stiffness matrix. In the next lecture, we will proceed from the structure stiffness matrix onwards, but hopefully the lecture will be direct discussion using Microsoft Teams, inshallah. So start working on this software. This seems difficult initially, but inshallah with practice you will be able to solve this program easily. Thank you very much.